Thank you. So hi everyone. So today we're excited to have Swati Gupta as our speaker. So Swati is actually one of my colleagues here at Georgia Tech. So she's an assistant professor in ISY, and she's also a Ford Family Early Career Professor in the department. And so she's also the lead of the ethical AI at the NSFAI Institute on AI for Ops. Basically before being here at Georgia Tech, Swati got a PhD in operations research from MIT. And in terms of research interest, she's interested in optimization, in machine learning, and in algorithmic fairness. And so today she's going to be telling us a bit more about her work on algorithmic fairness. And she's going to talk about mitigating the impact of bias on selection algorithms. So yeah, take it away, Swati. It's all you.
Thank you, Juba, and thanks for inviting me here. So today I'm going to talk about mitigating the impact of bias in selection algorithms. This is joint work with my amazing student, Jad Salem, who's also on the call, and my colleague in law and ethics, Devin Desai. So, okay. So here's what, just before I start my talk, I wanted to mention a few things about ethical AI at the NSFAI Institute. So we've been thinking about in our work across these 5 different research domains or big questions. So starting with theoretical foundations, what are the notions of fairness, multi-criteria decisions? We are looking at problems that could have a policy impact, such as districting, admissions, hiring, questions. And then the NSFAI Institute is also at Georgia Tech, and it's sort of inspired by applications that stemmed out of OR and could benefit from AI and machine learning. And so we're looking at sustainability of supply chains, electrical grids. And we are engaged in sort of interdisciplinary research and talking with policy, public policy, researchers on incorporating stakeholder voice and creating new processes for auditing and continual monitoring of the algorithms that are developed at the Institute. So we have PhD positions, postdoc positions, faculty positions. If you're interested, please get in touch. And we would love to, I would love to discuss that further. So in this talk, I'm going to talk about hiring in practice, basically stating some of the interesting developments that happened over 2020. So Microsoft, Wells Fargo, Adidas, and Google, big companies, they announced major programs to address racial disparities in employment in the summer of 2020. And they wanted to basically promote more Black and African-American managers, senior contributors, and leaders in the companies. However, in September 2020, we learned that the Labor Department actually settled, Microsoft settled with them for a few $1 million for alleged discrimination in hiring because of data from the last 3 years, from 2015 to 2018. And once the Labor Department actually saw these claims from Microsoft, Wells Fargo, Adidas, et al., they actually went after them to scrutinize, how are you actually going to increase racial representation in top senior management positions? So these set of cases, they talk about disparities in hiring and promotions, and gets to the question that, maybe we've all sort of heard about, the Title VII and anti-discrimination laws that prohibit the use of protected classes like race, color, religion, national origin, etc., in domains such as education, employment, housing, public accommodation, credit. And in this case, we are really worried about the domain of employment. And the question was, how can an entity such as Microsoft address this tension between disparate impact and disparate treatment? Because if they have, if they look at their past hiring processes, hiring practices, they see that they've created disparate impact because they've not hired people from minority and underrepresented communities enough. And if they actually look at the demographic information and make hiring claims with respect to those, they run into a disparate treatment problem where, again, they're at in a tension with Title VII. So this is what I want to get at. And I'm going to first discuss a mathematical model and then sort of get to why we think this might make a legal approach in practice. So let's first discuss modeling bias. We all know that there have been numerous studies on how data is biased. Certain demographics seem more employable, or they get more offers, or they get more callback rates, or they have more retention, and yada, yada, yada. So there's a lot of work that actually shows that there is bias in evaluations data specifically. And often we don't know that we cannot quantify that bias. We know that there is an estimation or an overestimation of certain numbers, but we don't know what the value of that bias factor is. We don't know how to fix that bias. And even though we know that there might be some under or overestimation of these numbers. For instance, these studies that I just sort of put on the slide, they were done by Claude Steele, who was managing, who's a professor of psychology. He started looking at admissions when he was at University of Michigan. And he saw that when students actually came from a stereotyped group and were asked to perform in a stressful environment on tests on subjects that were stereotyped, for instance, African Americans and women in math, then their performance actually went down compared to tests where they did not have any expectation or pressures created. So if we have all of these sort of psychological studies and even machine learning studies that sort of talk about bias, then the question is, can we actually make algorithms even when we don't know how to fix that bias? And there's been some beautiful work by John Kleinberg, Manish Raghavan on sort of creating the first models of bias that I had seen. And what we do in this work is generalizing that. So let me discuss how. So we propose a partially ordered set of bias model. So we call it a POSET model of bias. And the way we think about it is, let's say there are some candidates and they have SAT scores, or they have some interview scores that are available, or some machine learning algorithm is sort of creating scores for their resumes or predicting how hireable a person is. Instead of looking at these scores as real data, point-wise estimates, how about we think about these scores in the context of uncertainty around that score? So what you see in this diagram is, let's say we have candidates E1, E2, E3, E4, and E5. And I call these E's because I'm thinking about matroids and I'm thinking about elements in my matroid. But that aside, so these are candidates E1, E2, E3, E4, E5. And for candidate E3, I have a high uncertainty range. I don't know really where the evaluation could be, because perhaps I've never seen a person like E3 before, and I've never evaluated a person like E3 before. And so they have a higher uncertainty interval. Candidate E1 is somebody I've seen more candidates like, and probably I have less uncertainty about their evaluation. So candidate E1 score lies from 7 to 8.5, E2's lies from 4.5 to 6, and so on. Once I create these intervals, for instance, I know for certain that E1 is definitely better than E2, irrespective of how their true evaluation is, as long as it lies in that interval. However, with E2 and E3, there's no way I can compare these two candidates because I don't have enough data on them. So this is what a POSET model of bias might allow me to do. And it only tells me pairwise comparisons that can be made with certainty, and comparisons that cannot be made with certainty are just ignored. So we move away from an assumption that candidates can be totally ranked. Candidates cannot be totally ranked. There are some relations we can observe amongst the candidates we want to hire or we want to consider for admissions. And given those relations, we want to make sort of fair algorithms. Does this make sense so far? Okay, so this is an interval order, but POSETs are a bit more general than that. So our uncertainty intervals need not be just single dimensions. They can be multiple dimensions, and they need not even come from an uncertainty in the numeric data. So they could be just something that's exogenous to the model, something where you know that certain candidate is better or certain candidate is not at all comparable to another one. So let's look at an example here. So let's say we have candidates who are ranked by GPA in college and work experience. And by the different colors, I'm sort of pointing to different demographic groups or different backgrounds or something. And let's say this dotted line is the selection criteria that we have. So once we have the selection criteria, we are only selecting candidates who are, these blue candidates, and maybe, we are losing out on candidates because there was uncertainty. So our post-it approach will allow us to sort of draw uncertainty intervals around these candidates, and candidates where, let's say, their GPA intersects or work experience intersects, or you might have another criteria of constructing a post-it out of it. So given the uncertainty in the evaluations of these candidates, we can in fact then create a post-it, which is represented by a Haas diagram, where an arrow points to a candidate who's definitely better than the candidate from where the arrow originates. So from the pink candidate, you see that the pink candidate is definitely worse off than the top two blue candidates. But constructing a post-it this way actually now tells me that my selection criteria somehow must randomize across the two blue candidates and this green candidate who's also maximal in the post-it. If we were just looking at point-wise data, we may not have even considered the possibility that this green candidate was actually as competitive as the top blue candidates. So the way we are viewing this model of bias is that it allows us to detect possibilities. It allows us to move away from the most likely scenario. It allows us to consider errors in the data and really work with possibilities of what we can do in terms of increasing diversity, but that's really a nice artifact of this model. Okay, so an example of post-it is the group model of bias by Kleinberg and Raghavan in 2018, which was really nice and sort of motivated us to consider the post-it model. The group model of bias says, you have candidates in different groups, and candidates within a group face a bias factor that's specific to that group. And this is something that we actually also observed in New York education data. So we looked at SAT scores across schools in New York. And if we group schools by their economic need index, then we actually see a literal shift in the distribution by a factor of 1.25. So this is a very nice model that you can also validate across data. And this model is also can be represented as a post-it, because for each group, candidates are completely comparable within that group, but across groups, we have no comparisons available. What a post-it might allow you to do is now compare candidates across groups when you are completely certain that a 25%er in one group cannot compete with a 90%er in another group. So those comparisons now become available if you're considering a post-it. So it sort of gives a little bit more information than the group model of bias. And an example of this is what we call a network model of bias. And so we discussed sort of this hiring scenario with a new startup called LaborX. They market themselves as the LinkedIn for the linked out, and they match job seekers who can't really benefit from the LinkedIn network because maybe they didn't have a traditional computer science degree. And so here what we have is that you have some star nodes, and the distance to the node actually incorporates your bias is dependent on the distance to your star nodes. So if you're very close to the star nodes, maybe you give them a boost in their evaluations. If you're very far away from the star nodes, then your evaluations are not that boosted. But for some people where the external evaluation is still better than the internal rank evaluation, you can compare across those. And so you have these chains that are dependent on the distance from the star nodes, but then you also have cross comparisons across candidates if they came from a further distance, but a better evaluation than a closer distance and a smaller evaluation. Does that make sense? Okay, so if there are no questions on this, what we're going to do next is consider this post-it model of bias and try to see if we can design efficient algorithms and provide some meaningful interventions for hiring in practice. And we're going to do this through the lens of the biased secretary problem. And in particular, I guess people on this call are probably already aware of the secretary problem, but let me just recap it quickly. So let's say I want to hire select two people for Math Olympiad, and I look at their scores as they arrive. I know there are going to be 5 candidates, but I don't know the distribution of utilities or distribution of scores that I'm sampling my candidates from, or where the candidates could arrive from. So the first student is Pilar, and at this point, I don't have enough information to go forward. And at this point, I would typically ask an in-person audience to vote if they want to pick Pilar or not. So let's say we go on, and now we have Sam. Does anybody want to pick Sam? Okay, not really. And so the next candidate is April. Now we're really running out of candidates because we have 5 candidates overall. And so let's pick April. And the next candidate is Maya. Yay, so we sort of rectified our error with Pilar. So let's select Maya. But then we didn't even know that the scores were from 100, and Jad turns up with 110. So it's like, okay, we missed out on the best candidate. So the secretary problem sort of analyzes this trade-off between partial information and selection under maximization of utility under partial information. And the goal is to minimize the worst case comparative performance with respect to opt. So minimize the worst case opt over the performance of the algorithm. Now, all of our discussion on the bias in data sort of points to this question, like, what if some students had an extra job while they were preparing for this test? And, their 70 and 75 is actually biased in some way. It's an underestimation, but, should these students be actually considered more competitive than Maya and Jad, or are they competitive, do they raise up to 80? So we don't know a numerical estimate of how do we fix this. So we're going to consider a partially ordered set model of bias. And here's the secretary problem. Apologies for this extremely dense slide. So the setup is as follows. So individuals arrive over time. As they arrive, we observe their post-set relations with the candidates we've seen so far. And as the individuals arrive, an irrevocable selection decision must be made to maximize the total true utility. So again, we are given we want to select K candidates. So we're given K. We know that there are going to be total N candidates. We're given that. And we're not given anything else. As they arrive, we observe their post-set relations, and we need to make an irrevocable select or reject decision. And we want to be competitive with respect to any utility that's consistent with the post-set. So given a post-set, what we do is evaluate it against the worst case total, the worst case utility. So remember, like when we see the post-set relations, we don't see actually numbers. We just see whether a candidate is better or worse. So we see a post-set, and to evaluate it numerically in terms of a competitive ratio, we need to assign utilities. So we could assign any utility to the candidates that is consistent with the post-set. So it's any extension of the post-set into a total ranking with numbers. Okay. And so the secretary problem has beautiful connections to different settings and different, it goes back as far as 1963, when Dinkin gave an order E competitive ratio. And the idea of Dinkin's algorithm is super simple, and that's going to keep coming up. So let me talk a little bit about it now. So given that you have N candidates that are going to come in, the idea is to sample a few candidates at random. Based on that sample, create a threshold, and based on that threshold, select candidates after the sampling is done. And the candidates after the sampling is done can arrive in an adversarial order. So we only need the initial sample to be randomly generated. There are many variants to this algorithm. For example, Bobby Kleinberg in 2005 gave a very nice extension, whereas the number of selections of a secretary algorithm. So again, all of this is without considering bias. So the 2005 algorithm by Kleinberg is as the number of selection goes to infinity, the ratio actually also tends to 1. So you can actually get an almost optimal algorithm. And the way the selections are made is recursive based on a threshold that's dependent on K. And so there are many variants that work with non-strategic behaviors or extensions to matroid settings. And we're going to draw some techniques from some of these related works. And even talking about the fairness selection literature, there's been some very interesting work on modeling bias against different settings, looking at subset selection in an offline setting. But this work is sort of the first one to consider that in an online setting and also give the poset model of bias. So let me talk about algorithms. And one thing that's very clear is that, if we sort of ignore the group information or the poset information, we will perform extremely suboptimally. And because the bias is adversarial, because we're trying to minimize our worst case competitive ratio, any competitive algorithm has to hedge across different groups or different maximal elements in a poset. So let me talk about this in pictures. So here, let's say you have a group model. So you have a poset that looks like 3 chains for each of the groups. And you need to have some probability of selection across each of these groups. Otherwise, one of the groups might have an extremely high bias factor, and you might get a competitive ratio of infinity. So you need to hedge across these groups. And this is one of the design principles that's going to keep coming up in our algorithms. What this also means is that because, let's say I had to select one candidate, I need to hedge with a probability of 1/3 across these 3 groups. This also gives us an omega width lower bound on the poset secretary algorithm. So we can't actually hope for a competitive algorithm that's better than omega width because of adversarial bias in the problem setting. Good. So this is already nice because the way the problem is set up, we get that we need to have some probability. We need to hedge across the maximal elements. So it's sort of getting to what we might intuitively think as, as a nice, is a desirable property for selection of candidates. Okay. So let me talk about rank demographic parity formally. So this is what is it that we would want from a selection algorithm in terms of fairness? So we would ideally want equal opportunity to equally qualified people, and with an asterisk. So here I'm really thinking about equally qualified as equally qualified if I could just remove bias from every evaluation metric in the society, which is obviously not possible. So what we're positing as a fairness definition for the partially ordered model of partially ordered set of poset model of bias is rank demographic parity, where just sort of informally, we want the probability of selection to increase with better poset comparison. So if there's an element who compares favorably to another element, we want its probability of selection to be higher. And elements that are indistinguishable under the poset, so that are order isomorphic under the poset, should have the same probability of selection. So we don't want to introduce any eccentric ways of distinguishing between elements in the poset if they're indistinguishable due to an order isomorphism in the poset. So imagine one candidate. I should have had a picture here, but let's go back to this example. Let's say. Okay, let's go here. And in this setting, suppose there were 2 groups which had an equal number of elements. So this group 3 also had 4 elements and group 1 had 4 elements. Then the bottom 2 candidates of group 1 and group 3 would be order isomorphic. They would be indistinguishable given the poset. The second last candidates, or the top 2 candidates of group 1 and group 3, would be indistinguishable under the poset. So we don't want to introduce any other differentiating factors other than the structure of the poset. So this is what we refer to as rank demographic parity. And this already has connections to conditional demographic parity and somewhat of a calibration with respect to the poset due to the monotonicity of the probability of selection that it induces. So one nice thing that we can prove about rank demographic parity is that if an algorithm uses only arrival orders of candidates, and post-set information for selection of candidates. Then post-set information for selection of candidates such that the probability of selection is monotone under the comparisons with respect to the post-set. Then such an algorithm must satisfy rank demographic parity. So we want to use all the information that's provided by the post-set. We want to make sure that candidates who are favored by the post-set, who are compared favorably under the post-set, have a higher probability of selection. Candidates, and just that is needed to satisfy rank demographic parity. Okay, so let me go on with this, and I will point out where that theorem actually comes in useful. So let's start with a simple setting of the group model of bias. So here we have different groups and candidates arrive and their groups are revealed. So if just blindly, if we just had some probability of selection from every group, then we need to have some probability of selection from every group. We cannot toss a coin and just select from one group. That would probabilistically be fine. It would not be fine ex ante. And so what we could do is we could say, okay, we want to select around 1.2 candidates or around K over G candidates from every group. In the earlier slide, I had K and G set to 6 and 5. So that gives me 1.2. So I could select sort of proportional candidates from every group. That gives me the right competitive ratio, but this is very theoretically restrictive in terms of setting quotas. And this does not work when the groups are adversarially assigned. So let me actually talk about a solution for this case. So again, the setting is as follows. So we know there are going to be 3 groups. We don't know how many members are going to arrive in each group. Groups can be adversarially assigned. Utilities are adversarially assigned. We only see comparisons as candidates arrive. Okay. So there are total n candidates. And the first thing that we can do is actually use a technique from the Metroid secretary literature by Jose Soto in 2013. It's a very nice technique that is actually used to understand secretary problems over uniform matroids. And so what we do is, as the candidate arrives, we observe their group membership. But for now, we ignore the group membership and we just give them a label. So you can think of this as assigning the candidate to a random interview committee. We have, let's say we want to select K candidates, then we have K interview committees set up at random. We send a candidate randomly to one of the interview committees, and each interview committee is directed to select best single candidate across all the groups. So they can see the group information, but they only select one candidate per interview committee. This gives us a competitive ratio of G+1 times E squared. And so in some sense, we are sort of losing a factor of E because of the use of labels. And I'll talk about it in the next slide on how we can remove that if K asymptotically goes to infinity. So it's a non-tight competitive ratio, but this is the best we have for a finite case setting, for a small case setting. Okay. So the setting gets easier if we have random group assignment. So in the previous slide, I considered adversarial groups and adversarial utilities. So if we have random groups, then things get easier because now each group has a big enough size, and our initial sample, our initial sample sort of tells us what the size of every group is approximately, and we can simply use Chernoff bounds to bound the number of people in every group. Again, this is still inducing a quota, which is not great, legally speaking. I'll come to that. So this algorithm has an order EG. So just moving from adversarial groups to random groups, we are able to reduce that factor of E. And we are able to reduce that factor of E again. We are able to completely get rid of the G bound if our group assignments and utilities are both random by simply using this idea. So the idea is to look at the different groups and parallelize a vanilla secretary algorithm on each of the groups. So that's the basic idea. But at some point we have to use Chernoff bounds to get the right numbers, or we have to do some estimation. The adversarial setting is more interesting because we had to use labels in that. For these algorithms, as K goes to infinity, we can extend and get an optimal an order optimal competitive bound. So we are able to get an order G as k goes to infinity. Remember that G is the lower bound. So we can't improve on G under the bias model. So all of this was a warm-up for the POSET stuff. So group model is nice and it's easy to analyze simply because the POSET structure is very simple. We just have K chains. We have some G chains that are already given to us. If we observe the group membership, we know which chain a person belongs to, and we can parallelize our algorithms on that. For the POSET bias model, things get a little bit trickier because our goal is, remember, it's to select elements that are maximal as they arrive. We want to select the maximal elements overall in the POSET. So our probability of selection of E1 should be higher than the probability of selection of E2 and E3 and so on. And one way that we can think about the POSETs is, it's just a group model of bias with some more comparisons. So if you see this block of elements, E1, E2, E4, it's what is known as a chain. And so we can decompose this POSET into a set of chains. We can decompose it into the width number of chains. So what is the width of the POSET? The width of a POSET is, if you look at a set of elements that are mutually incomparable, the maximal set of elements that are mutually incomparable, the width is the size of that set. So here, what is the width of my POSET for this example? Well, E4 and E5 and E3 are mutually incomparable, right? We don't know what the comparison between E4, E5, and E3 are. And so this POSET can actually be decomposed into 3 chains. So that is the theorem of Dilbert's, that any POSET can be decomposed into width number of chains. So if I decompose a POSET into these chains, I could think about this as a group model of bias again. And of course, I don't know the POSET upfront. So a chain decomposition is hard. You can do it in an online manner. But such an algorithm induces these eccentric relations across different elements because of the chain decomposition. So that's completely unspecified by the problem, right? It's completely something external that we are adding on, external as a structure that we are adding on, because different chain decompositions would induce different probabilities of selection. And that sort of violates our rank demographic parity. We don't want any of these spurious probabilities to prop into the algorithm. So this reduction to the group setting actually does not really work for POSETs, and it doesn't give us algorithms in the that satisfy rank demographic parity, even though we can give competitive algorithms. So here we needed new techniques. And the way we get around all of this sort of chain decomposition issue is by directly working on the POSET, even though the width and some parameters are unknown. So what we do is we estimate the width of the POSET. So we first take a sample of the POSET, and that sample should basically give us an estimate of how thick or how tall that POSET is. So what is the width? What is the maximum number of incomparable elements in that POSET, mutually incomparable number of elements in that POSET. Once we have an estimate of the width, we decide whether our initial sample was big enough or small, and we sample more elements accordingly. Once we have that, we are able to adapt this labels technique to the POSETs again. So we are able to adapt the labels, and we assign a label to candidates as they arrive. And as we assign these labels, we make sure that each independent interview committee in these labels is selecting the maximal candidate that it sees beyond the sample. So that gives us the POSET model. Of course, now there are multiple levels of analysis, and it becomes a little bit trickier. And each of these levels of analysis adds a factor of E. So because we estimate the width, we have an E. Because we have labels, we have another E. And because we are using a secretary algorithm, we get an E. So we get an E cubed. That's the last row here with the gap K POSET. Omega is the lower bound, so we can't avoid that. If we knew the width, actually, we could get an E squared because we removed that one level of estimation. And it's an open question currently on whether we can get an order omega competitive algorithm without these E factors. Even as K goes to infinity, that's open. We're able to extend that approach to very structured set of post sets. So the nice thing about our work, which I really like, is that many of the takeaways are managerial. So these are things that can actually be implemented in practice. Even though we viewed it from a very theoretical computer science lens, we can draw some managerial insights like take estimates from prior samples, have independent selection committees that are randomly assigning candidates to the different committees so that your bias sort of operates independently, and some committees are still able to select, some of the top candidates. Selection of best candidates in each label is in each independent interview committee is nice, and to not disregard any comparative information, because then we are not satisfying nice properties such as rank demographic parity. So we don't want to actually reduce post sets into chains and then use a simple algorithm for groups. We don't want to do that. We want to make use of as much information as possible. So a lot of open questions. For instance, gap K post set factor of E cubed is something we don't like, and we would really like ideas to get around that, or would be open to listening to extensions for that. We don't know how to extend these algorithms without the knowledge of N. So when we don't know what the total number of candidates are, and that seems to be a big open question, and just the secretary literature in general. So with that, let me quickly talk to you about an experimental case study, and then we'll talk about the legal implications of this. So we considered an aspiring minds employability outcomes data set from 2015, where candidates had self-reported features that you see on the top of the slide: gender, 10th percentage, 12th percentage, and so on. And we looked at computer programming scores by gender. So the plot on the left does not show any, it shows very similar distributions across females and males, and there is no skew in the computer programming scores. So we said, okay, so we have all this data. How about we use a machine learning model that predicts computer programming scores? So we predicted computer programming scores. So this is a linear regression. It's nothing fancy. This is really like a proof of concept kind of an experiment here. So some machine learning model, this has some bias. The gender variable is assigned minus 16 points. So everything else being the same, if your gender is flipped, a candidate might lose 17 points in the prediction. And so we see that the model has picked up on some skew in the underlying data. And we see this in the plot on the right. Right. So the model picked up some implicit bias in the data that was not observed when we just plotted distributions of computer programming scores. But now we are predicting those and using that as in how hireable that person is. So now if we were just to use a vanilla algorithm, that's the plot on the left. You see that the male selection rate versus the female selection rate, it's off by 100%. The male selection rate is twice that of female selection rate. But if we construct post sets, so that's sort of a big, I guess, it's a nice research question here. How do you construct a post set that's meaningful for models where you can't observe a lot of, the model is not as transparent as a linear regression model. So for this linear regression model, we constructed a post set that you see on the top. So the triangle is actually the predicted score, and it's a little bit left of the middle because we are considering multiplicative bias. We estimate that multiplicative bias, and that's like a 16 or 16.95 interval that you see here. So we construct this interval post set, and we use that for the selection, and we see selection rates are actually quite nice. And think of it this way, there's a lot of work in fair ML and fair theoretical CS that talks about audits, that talks about not using protected information or using an auditor for that. So what if a third party or somebody, some auditor is actually giving you a post set. An auditor is able to say that this candidate should be compared favorably to this candidate, or for these two candidates, actually we have no way of comparing those. That's all the information the algorithm is using from that point onwards. The algorithm is only using the post set information, not the evaluations, not the group memberships, nothing else. So in that sense, it's nice, and we see for this data set that the selection rates actually now start looking more similar. This work was, a preliminary version was accepted to Wine last year, and this is currently under major revision in management science. So let's talk about the legal aspect. Sorry, I've been talking nonstop, so if there are any questions, I'll pause for 30 seconds and create uncomfortable silence.
I have a question, but I really want to hear what you're going to say about the legal aspect. So I'm going to wait.
Okay, awesome. Okay, I'm also very excited about this part. So we constructed this partially ordered set model of bias, and we had this experiment, and we started talking to our law colleagues, and Devin got super excited about this. So over the last 1.5 to 2 years, we've been sort of just tearing our hair apart in translating things and understanding what can we say and what does the law say. And I'm sure many people here have had the same experience. So what I'm going to say before I present these slides is a lot in the law depends on the context of the problem. And I'm going to talk about some cases that we can draw precedents from. And I'm going to set up a scenario. So every time there's a CEO who's asking a question and we are responding to that question. So my concern is that workforce underrepresents women and minorities. What is the first step that can help remain within legal constraints? So the first thing is that we found cases where it actually helps to diagnose and document imbalances and potential built-in headwinds. So the law definitely does want to remove potential built-in headwinds for minority groups. So these headwinds can be done for job categories that are traditionally segregated. So you can use that and say that, for these STEM jobs, actually, we don't get a lot of underrepresented minorities who belong in these demographic groups. And I have realized that actually my company is creating more of this disparate impact. So it actually helps document and diagnose these imbalances, because then the companies can make a case on proactively implementing certain measures to reduce these built-in headwinds. So that's first step. Okay, yes. So, we've documented there's an issue. What can I do about it? We just don't get good underrepresented minority candidates apply for our jobs. And that's an argument that I have also heard many times in a lot of hiring related contexts. We just don't get good enough underrepresented minority candidates. And so this is a big issue. And the question is, are you operating under a biased evaluation? Are you certain that what evaluations you're seeing are actually exact? They are free from bias or uncertainties? Is there a consistent worrisome trend in your data or models? And that has to be diagnosed and documented and dug into a little bit more. So for instance, the study on the SAT scores, where we saw that there was a definite shift if you changed the economic need index of schools, or the study on gender dependent computer programming scores. So digging into your data and models to see whether the uncertainties are there is a good thing, because it's going to help us in the next steps. So we do see women candidates get consistently lower ratings, but when talking to managers, we cannot tell why there should be any difference. So, okay, so maybe, the way I'm setting up the context is there was some documentation, there was some digging around that things are not operating the way that you would expect them to. Once this happens, construct a post-set. So what the law appreciates is something that is a due process. And this is where the post-sets can help, because if we can document the uncertainty in evaluations data and we can back it up by the processes in the company, then we can make a case that, look, the evaluations are uncertain. At this point, my algorithm is actually treating that uncertainty in a very transparent way and selecting candidates in the best way possible without enhancing those disparities. This is too much of a hassle. Why don't I just use the 4/5 rule? And I guess a lot of people have heard about this. There have been a lot of studies, in fact, over the last years. Let's just do the 4/5 rule and select at least 4 women for an interview whenever we interview 5 men. And this is something that, a recent study by Raghavan, Kleinberg, Borakis, Levy in 2020, they actually looked at various hiring managers, hiring resume screening, third-party vendors. And they saw that a lot of them actually use the 4/5 rule. But the 4/5 rule actually doesn't solve the bias problem. It will not fix the hiring pipeline. It is only a trigger for checking for discrimination. It is only a trigger in the law. It says, okay, if you violate the 4/5 rule, we'll just check whether there's something discriminatory that's happening. And it's not It's not going to fix the pipeline problem. It's not going to fix the final hiring decisions. It's not going to fix representation. So it's actually getting around that problem without really addressing that problem of biased evaluations. And okay, so tell me why a post-it approach might work. And so now these are some of the legal arguments why we think that this is actually implementable in practice. So construct in a way that's mathematically justified. This is important for due process. And the key point is that an employer is allowed to examine how to design a practice in order to provide a fair opportunity for all individuals regardless of their race. And I actually, if there's any time or if there's any interest, or if people have actually heard about the Ricci v. Di Stefano case, then I can discuss that in the discussion. I don't have a slide specifically for that. This case has created a lot of confusion in the current literature. And we dug into this case a lot more over the last many months. So I'm happy to talk about that in the discussion. So post-its allow us to give the candidates a benefit of the doubt to all the candidates, irrespective of the demographic group. So we can construct post-its by clustering candidates or by looking at how varied evaluations were for those candidates. And there is precedent that law does not like treating people as numbers. So there is precedent that, if you're just making decisions based on numeric data, law will most likely not like that. So here's Johnson v. Transportation Agency case. So here's what happened. 2 candidates were deemed to be well qualified based on a range of metrics, such as experience, background, test scores, and they had, it was a company where they had a threshold for being promoted at 70, and there was a test. So the man scored 75 on that test, the woman scored 73. Okay. Now, the expectation was the man would actually be promoted, but the company had a holistic evaluation and they promoted the woman instead. The man sued the company on discrimination, on reverse discrimination. And the court actually sided with the company because they said the company, it was just a threshold. It was not a criterion for promotion. And law does not like treating people as numbers. So the company actually took a holistic view of what it meant, who had a better impact. And it was not a blind hiring plan. So that it dictates, that is, if a plan dictates hiring solely by reference to statistics, if a plan does that, then it is not likely to be allowed. So this gives us somewhat of a bolder precedent to sort of argue that post-its are legal. There are other aspects of this. So understanding why is post-it not like a quota? Are you constructing intervals to give the benefit of the doubt to some candidates and not to others? So post-its, actually, if you're constructing a post-it, then as long as you're following due process and not actually looking at the demographic information specifically and saying that you have to hire a few people, some fraction of people from a certain demographic group, it is not imposing a quota. Once you have a post-it, the selections from that post-it really depend on the distributions that you see in the data. And it could actually help the majority group in some sense. Like, let's say in this example, it could actually help hire more male candidates. It could increase representation in some distributions of data. All we're saying is that this allows us to be very transparent about the uncertainties that we have. And if we do use post-its, when can we stop creating them? And this is a question that legal scholars often like to answer in terms of approaches. Because I don't know why it keeps going to the next slide. So the question of when do we stop? Like, are we there yet? That's a question that a lot of legal scholars want to understand for any approach that's proposed. And for post-its, the nice thing is that if the uncertainty in your data automatically reduces as you gather more data on candidates, or you invest resources to have maybe an extra interview or a training plus an interview on certain candidates, and you reduce that uncertainty interval, then your post-its, the width of the post-its will automatically shrink, and you will sort of revert back to using total numeric data. So it's nice. It's sort of adaptive to the uncertainties in the process, and that's something that's considered a positive legally. So just generally speaking, what is allowed in the design of bias-aware algorithms to improve the yield of who to interview. Again, legally, there's a lot about responsibility. So if you're screening for resumes, it's a third party, which is not liable for making hiring decisions as a company. So there's a lot about who has a responsibility in the different steps in the process. And here are just some sort of very quick takeaways from all of our digging into this. Blind hiring is not allowed. So just don't rely on numbers. It must be a multi-factor plan. It should not insulate an individual from comparison. So this is what a quota does. It insulates from comparison because you say that, oh, I have to hire 5 people from this group, irrespective of how they compare to other candidates. And the comparison does not require a pure numeric ranking. So, okay. So these are some points to remember. And with that, I think I'm almost over time. Almost on time, and I'm happy to take questions. So I guess like, okay, so just one last thing, right? Like we started with an interesting mathematical question. We said, okay, we are interested in bias and fairness and machine learning models, and all of this ranking data for admissions hiring, this is all biased. Can we model that? Yes. Okay. Partially ordered sets. Yay. That's a nice model. And then we looked at an interesting problem from just a theoretical perspective of online secretary problem. But the interesting thing is how relevant this has gotten over the last years, and sort of the legal takeaways go way beyond just the secretary problems. The legal takeaways sort of go into just understanding uncertainty in your data and being transparent about it, and perhaps creating fairer decisions or more representative decisions along the way. So, okay, thank you, and happy to take questions.
Okay. So I think you've answered this in your summary, but let me just ask just to be sure. Your key ideas would apply also in the non-online, but the batch case. Yes. You have a pool, right? Okay.
In fact, I would go even further than that. They would apply to not just hiring, but for other domains as well, where you're sure. Selecting candidates.
Sure. Mm-hmm. Mm-hmm. Okay, thank you.
Thank you.
Oh, you said you would be, I forget the name of the case, but the firefighting case. Mm-hmm. You said you would be able to speak about that in the Q&A.
Yes. Yes. Should I? Okay.
Please.
So the Ricci v. Di Stefano case sort of created this narrative over the last few years that disparate treatment is not allowed. So what happened in the Ricci case? There was a firefighting company. They spent a lot of resources. They went through due process. They created a test that would not create disparate impact. So they created a test that would presumably be fair across different demographic groups. And when they administered that test, so they advertised the test, they said, if you pass this test, we will promote you. When they administered that test, so people, okay, before administration, people prepared for that test and they gave the test. Once they gave the test, they realized that there were no African-American firefighters who were selected in that. Right. And the company was sued. And so they said, okay, this test actually seemed to create disparate impact because we didn't have any African-American managers, African-American firefighters selected. So let's throw out that test. So a few things happened here. So first is they created a test with due process. They claimed they invested resources. They created that. The second thing that happened was when they announced the metrics of the test, people prepared invested resources. The third thing that happened was once the test was administered and thrown out, they created visible victims. The people who sued the firefighting company, I think one was a Latino and one was a white American. So what happened was, so now once you create visible victims, it created this notion that, throwing out that test was not, even though that test created disparate impact, it was thrown out and the company lost that case. But this is not what happened because it happened with these three parts of the context. So if there is due process, then you can actually make a claim, you can make a claim that this is why I'm treating these people, or this is why my algorithm is treating everyone in this way. For instance, a post-set approach. The post-set approach might say that, uncertainty on these candidates is higher, but as long as this is sort of justified in due process, it is not as black and white as, okay, I can't have disparate impact or disparate treatment.
What would have prevented you from getting into the situation that Ricci was in the first place? But your work has nothing to do with handling Ricci ex post facto, or how someone could have argued differently.
So for Ricci, I guess what we discussed was, and Jad, you can feel free to chime in if you want to add more to this. But had they not done the test, had they not invested resources in that test, mm-hmm. and then they'd thrown out the test and said, we are going to do it, that would still have been, okay, let me take it back. Had they just tested on historic,
taking it away. The key thing in Ricci was taking away the win, right, after the win had been awarded.
The visible victims, right? So if I had tested on historic data, mm-hmm. and I had not, let's say I'm the firefighting company, I had an algorithm, I tested on historic data, I saw that this is not actually selecting any people from underrepresented minority groups. And then without announcing what the metrics of the test were, I sort of went in my machine learning training testing loop and sort of said, okay, let me change my algorithm, or let me dig into the data, let me do some other process for handling this. That would have been okay. Here it got complicated because of visible victims. It got complicated because they claimed it was due process.
I think the other thing with Ricci is that it is just the fact that disparate impact is not necessarily illegal. Like they spent a lot of time trying to validate the test and make sure it was fair. And because of that, even though there was disparate impact, it probably would have been okay.
Yeah. Thank you. More questions?
Okay.
Well, yeah, I guess we don't have any more questions. It's like already past 1, so I guess we can stop